Okay, so welcome back. Last time I'd given uh, a list at the end of kind of the big names at the end of Alexandrian mathematics. So this period is roughly from 200 BC to 500 AD. So here are the big names. So Hipparchus, Heron, Menelaus, Ptolemy, Diophantus, and Pappas. Pappas being the last major contributor to math. And there are some lesser contributors as well here that I'll mention briefly. Mostly, you could say like what makes them lesser. Mostly, their contributions um, were primarily through commentaries. So they wrote commentaries, and some of these were influential in the sense that those commentaries are what survived and what were later translated, and so they did a good job of actually preserving some of these works. Proclus, for instance, was we had mentioned this name previously. A lot of commentary. So Proclus wrote commentary on Book One of Euclid that passed on a lot of knowledge for, or at least attributions for how things were done by the ancient Greeks, at least according to Proclus. Of course, as you see, he's writing a lot later here, but uh, a lot of what we claim to know about some ancient Greek mathematics actually comes from the commentaries of Proclus, drawing not just from Euclid but from other sources, which many of which have been lost. So anyway, so typically, I believe all of the Nicomachus actually wrote. There's actually some works that survived of Nicomachus that's mostly number theory stuff. That so I actually have a copy of one of his major works, but the rest of these primarily were responsible for commentaries on existing works. And so these are the big names. And as I mentioned last time, you see that over this span of all these years, there's just not that much stuff going on, right? Compare this to the list of names that you could list out, from say 400-ish BC, or if I go back even a little further, maybe like 490, right, ish BC, to to 200 BC, that span of 300 years has like a huge list of names of contributors to math, and this is a span of 700 years and relatively small list. Which also begs a question that I'll bring up again, which is you might be noticing, right, comparing this list and the time scale with maybe what you know about the history of the Mediterranean or the history of Europe from the early, or the early Middle Ages, right? Or starting with say the fall of the Western Roman Empire. You might compare some of these and notice that it seemed like mathematically contributions to knowledge were drastically decreasing, right, in their importance, even before the fall of the Western Roman Empire, and that's certainly the case. That's certainly true. And so, it is a mystery somewhat as to why that is. This is a very interesting topic that I'll mention when I bookend this segment. So, especially when I talk about, we had previously mentioned the library at Alexandria. If you know anything about the history of the Library of Alexandria, you'll know that while, supposedly it was, the library was, destroyed by invaders, is this is actually not that accurate of a story, since it was known to be like in great disrepair and great. It was essentially something that had already been destroyed over the years. This was something that by the time of the supposed invasions, when it was destroyed, it was already something that essentially didn't exist in its old form. And again, you could tell this by the decline in quality here, and the contributions being just less and less from the mathematicians there. So anyway, going in order here. So what was Hipparchus known for? So Hipparchus's main contribution. Well, I shouldn't say. There was a lot of things that Hipparchus did. So some of these things were refinements of earlier knowledge. So just copying again, Hipparchus of Nicaea. So this is he was born about 180 BC. So a couple of things. I had mentioned previously how Eratosthenes had computed things like the axial tilt of the Earth. Hipparchus computed this to within a very high degree of accuracy. So computed axial tilt of the Earth to high accuracy. So this is stated as the angle between the ecliptic and the equator. The ecliptic being the plane of rotation, right, of the Earth, and so this is the angle between the ecliptic and the equator. So this had been known there were attempts actually even before Eratosthenes, I believe in about 350 BC. There was I can't remember the name of the first person to make this measurement, but essentially this measurement was made originally by the ancients using a sundial. So using a sundial, measuring the shadow of a particular sundial on the solstice was the thing that was done to estimate what this axial tilt was, and it was found to be like pretty accurate. I can't remember exactly how accurate that original 350 BC measurement was. Eratosthenes said, I believe, that it was 23 degrees. We know that it's about 23.4 degrees, and it's slightly changing, but it's about 23.4 degrees. Now, and Hipparchus was pretty close. This was pretty accurate. In fact, based on Hipparchus's, it wasn't until Arab mathematicians, I believe in the 800s, that arrived at a 23.5 degree measurement, based on Hipparchus's methods of doing this. And so this is a pretty accurate description of this fact. Also, the duration of the year. So computed the duration of the year to within 6 minutes of accuracy. So that's pretty good. Okay. He computed the precession of the axes, or in this context, the precession of the equinoxes. He computed lunar parallax. Okay. Eccentricity of the solar orbit. Okay. And thus he noted this fact that the orbits of the heavenly bodies in question, so for instance like moon and sun, so these orbits, especially the orbit of the moon around the Earth, he noticed that it wasn't really a circle. It was just almost a circle. And to attempt to describe this this motion, he introduced epicycles, which are like almost circles, in a sense, which was an attempt that would be taken up later by someone who was also in this earlier list, Ptolemy, to attempt to salvage this kind of idea coming from Aristotle, that, you know, the perfection of the heavens, right? The perfection of the heavens being that there were these circular orbits, right? All these planets had circular orbits. Of course, as even the ancients noted, this didn't match up with the actual observations of the motions of the heavenly bodies. And so to try to salvage the idea of circular orbits in some sense, the introduction of epicycles was done, which were these kind of sort of circles, right? Now you might be saying, well, isn't a kind of sort of circle really an ellipse? Yes, but you know, the idea of elliptical orbits was not something that had been put. It had been put forward by earlier mathematicians. I can't remember the name off the top of my head. I'll have to look back in my notes. But there's actually an earlier mathematician that I mentioned previously in the batch of mathematicians right before I talked about Archimedes, who had suggested elliptical orbits. But the idea was that these epicycles were intended to kind of salvage the idea that the orbits were somewhat circular. Okay, and of course you could talk about epicycles of higher order to get more eccentric orbits. Okay, and this is actually what Hipparchus suggested for talking about this stuff. But so while all these are very impressive astronomical achievements, as I said, many of these had been computed or at least approximated previously, especially the axial tilt. Like I said, this was the first really good approximation of this was done by Eratosthenes. One of the biggest contributions of Hipparchus is that he founded trigonometry in a way that we can say is, you know, equivalent to the modern understanding of trigonometry. It won't be until we talk about Indian and Arab mathematicians that we actually get trig in the sense of sine, cosine, and tan functions in the way that we're used to. As I had previously mentioned, Indian mathematicians use sine and versine in a similar way that we use sine and cosine. Versine being like 1 minus cosine, I think. And Arab mathematicians had used sine, cosine, and tangent in the exact way that you would have been, you know, introduced to them when you were first being read Sakatoa. So the idea is the following. So Hipparchus introduced trigonometry. And when we say trigonometry, we mean trigonometry in terms of the trigonometric functions, the idea being that you begin with unit circle. So he did exactly this. So you begin with unit circle that has radius, or that has center, we'll call the origin. So it has radius 1. So let's take a point here on unit circle, which is A, another point on unit circle, which is B, right? Okay, and so the idea is that I have some segment here. I have triangle, if you like, ABO, but I also have the length of this chord here. Right? Okay. And if I am thinking about, say, this distance being 1 here, right? I want to talk about this angle, say, theta. Okay. If I want to compute length of chord, okay, how would I do that? Well, the idea is that if I have an angle measurement, so let's say that my angle measurement, let's say angle AOB, that I'm calling angle theta. So theta is angle AOB. Let's say that that's like 30 degrees. Okay. So then what is the idea? The idea is to associate to this angle, we're saying that this is like 30 degrees, to associate to this angle a length of a piece of unit circle. Okay. Okay. So, of course, it's not the actual length of the unit circle that I'm interested in. It's this chord here, this segment. Okay. And so how would this be done in terms of the angle? All right. And so the idea here is to write, well, the chord, right, of 30 degrees. All right. So the chord 30 degrees here is equal to some quantity. Well, I would need to figure out actually what the length of this thing is. And let's say that I could compute that the length of this thing, and in fact I can compute that the length of this thing in this case, all right, this could be directly computed, that this is like a 31.06 over 60. So I would say that the chord associated to the angle 30 degrees is 31.06 over 60. Okay. And what I could do is I could fill out a table with values like this, right? I could fill out a table with values for different theta, right? For different angular values. Okay. But what is this? What is it that I'm actually filling out here? What I'm actually filling out, right, is chord of theta. What is the thing I'm actually computing? Well, if you actually trace through this and put this into modern terminology, we're saying that chord of theta, this chord function, is actually 2 times sine of theta over 2. And so when Hipparchus was writing these entries, chord of angle is equal to some length, and putting that in a table, what he was actually computing was this. He was computing the sine. Now, yeah, there's these little correction terms here, right? It's a half angle thing going on here. But what was being computed by this chord function was actually sine. And so he was putting together the first tables of sine values, right? Okay. Since we know that now the relationship between sine and cosine, this is equivalent to coming up with values for cosine as well, right? If you know sine theta, then you can figure out cosine theta by the Pythagorean identity for sine and cosine. And so this is a trig table, right, that you're generating here. So that's what Hipparchus was doing. Okay. And so in generating these tables, he also used the following formula. So he also used, in filling out these tables, formulas like this. This isn't the only one, but this is one that he certainly used in generating these tables. So recall these sine, angle, and difference formulas, right? So sine x cosine y plus minus cosine x sine y. Right, that's what we get for the sine, sum, and difference formulas. So he also displayed that he knew this and this power reduction formula, that 2 sine squared of x over 2 is 1 minus cosine x. So these formulas that might be vaguely familiar, right, from either trig subs in calculus or all the way back to high school trig, these are things that were understood by Hipparchus. Okay. Now, as I said, it wouldn't be later until Indian mathematics and Arabic mathematics that we get full-blown trigonometry in the like completely modern sense. But this is already very close, right? Okay, and so this is how his tables were constructed. Okay, all right. So this is the main contribution of Hipparchus to mathematics. His other contributions were mostly astronomical. But this was his main contribution to mathematics. This is going to come up again immediately here in a second when I mention Ptolemy, who used a very similar method for generating trig tables. And so Heron of Alexandria, so this is to remind you, Heron of Alexandria was active about 60 AD. So he's known primarily for Heron's formula. Now, this formula is named after Heron of Alexandria. It was probably due to Archimedes, but it's named after Heron of Alexandria, and he definitely wrote it down. So while it may be due to Archimedes, he gets tentative credit for it, and I don't think anyone's coming to reclaim his credit for this equation. This is a really nice way of writing the area of a triangle in terms of its side lengths. So we know how to compute the area of a triangle, 1/2 base times height, right? But if your triangle is not a right triangle, then the height is not apparent just from the side lengths, right? So if I throw down a triangle to you, right? So maybe let's just take random triangle, maybe looks something like that. That looks a little bit closer to a right triangle than I wanted, but let's just say that it's A, B, C there. Because I've labeled it like this, you know it's not a right triangle because it didn't make that longest side C, right? Okay, so I have triangle ABC. I want to come up with a formula that computes the area of this in terms of A, B, and C. Okay, so how do I do that? First, I define this quantity S, which is A plus B plus C divided by 2. Okay. So I take the side lengths of this triangle, I sum them all up, and I divide by 2. Okay. Then what? So Heron's formula says that the area of that triangle, given with those side lengths, is the square root of S, that's this quantity, times S minus A, times S minus B, times S minus C. That's an interesting formula. So I'm going to leave it to you to try to think about why that might be. Okay. This is known as Heron's formula. Okay, so this is a pretty neat formula for the area of a triangle without referring to some altitude, right? Some height cutting through, forming right triangles here. Okay, so this is nice. Okay, that's primarily what Heron is known for, is that formula. Okay, Menelaus is similarly known for basically one contribution. So reminding you, Minellas of Alexandria was active around 100 AD. So he's known for Menelaus' theorem. So before I mention Menelaus' theorem, so he was apparently the first to study spherical trigonometry. First to study spherical trigonometry. So this was, I don't have my nice sphere in front of me anymore, but this was the thing that I'd hinted at before when talking about possible models for non-Euclidean geometry of what is the proper notion of a triangle on a sphere, right? And this is arcs of great circles. And if you study the trigonometry that results, you'll quickly see that, right, it's possible to have things like a triangle that has 3 right angles. Is something that's possible. So Menelaus was the first to study spherical trigonometry. He's also mostly known for the following. So this is Menelaus' theorem. And so rather than write it out, it can be a little bit complicated. I'm going to draw the picture, and I think that's probably better than me writing out this paragraph and giving you conditions on it, because it can be confusing to try to keep track of what's going on. Let's start out with a triangle. Like this. So here's my just generic triangle. We'll call this ABC. Okay, so we have ABC. Let's say that we have a point D that is on the line through B and C. Okay. So here's the line through B and C. We're going to say that D is here. Okay, but I want to clarify that this point D could just as well be here. Okay, it could be on the triangle itself, but I'm going to put it off the triangle. Okay. All right, let us draw the line through A and B and A and C. And so, through A and C, I have a line, and I have a point E that is on this line. Okay, so maybe my point E is like here. Okay. Again, what is true for the previous thing that I wrote is also true here. This E could be on the side of this triangle. All right. It could also be over here, but I just drew it so that it would be right there. Okay. And then lastly, I have a line through the points A and B here, right? And through that point, okay, I can draw, or through this line, or on this line, I have another point that I'll call F. Okay, so I'm actually going to put it, extend this a little bit more, and then I'm going to put it like right here. Here's F. Same thing that I said before. It could lie on the triangle or not. But what I'm going to say is that either 2 or none of D, E, and F lie on the triangle. This is an assumption. So assume that either 2 or none. So 2 of these points, D, E, and F, could be on the triangle. Right? If D and E are on the triangle, then F isn't. Okay, so but any 2 of them can be. All right, or none of them are on it. So we're in the case that none of them are on it. Okay. Then, what does Menelaus' theorem say? So this is the configuration. What does Menelaus' theorem say? Then, D, E, and F are collinear if and only if BD times, this is the length of BD, times the length of CE, times the length of AF is equal to the length of CD times the length of AE times the length of BF. Okay. So it's very hard to look at this picture and actually see what it is that is going on and why this might work. But actually, working through this is not as tricky as it seems. Basically, once you kind of ignore the picture and set up the ratios you need, once you see how the algebra works here, this is actually not that hard to prove. So I may do this, or I may guide you through this on an upcoming assignment. But this is the idea. Now, the reason I wanted to mention Minellas Theorem specifically is that this is used as a way of proving another named theorem that I'm going to mention today, named Pappas Theorem. This is one of the ways to do Pappas Theorem. It's not the best way of doing it, but it's actually, I believe it's the way that Pappas originally did it, and it is there's a couple of ways to do it. You can also do it using similar triangles, which is another easier way to do it. The easiest way to do it by far is using linear algebra. So adopting the French method of the annihilation of triangles and using linear algebra instead is good for Pappas' theorem. It makes it a lot easier to prove. Otherwise, proving it with Minellas' theorem is kind of convoluted. But anyway, this is Menelaus' theorem. Okay. All right. And so that brings me to Ptolemy. As I mentioned previously, this is a name that you've likely seen if you have read anything about the history of science, if you've taken any astronomy classes or any class where the general progress of astronomical knowledge has been shown. The Ptolemaic System, as it would be called, was precisely the thing that would be held up by the Roman Catholic Church as how the universe worked. It was the thing that Galileo, got in trouble for railing against. It was the thing that Copernicus, was basically saying, was wrong. And it's the thing that Kepler ultimately demonstrated was false, was wrong. And so, what was the Ptolemaic system? Ptolemaic system was an astronomical system that gave or tried to give an account for why the motions of the heavenly bodies looked the way they did. Okay, and it was very much an attempt to kind of reconcile some Aristotle influenced ideas with the actual observations of motions of these things in the night sky. Okay, and so Ptolemy died in 168 AD. Again, not to confuse this Ptolemy with the much earlier Ptolemaic ruler of Egypt. So this Ptolemy lived very much in the Roman Empire. So what he was known for is a work, Almagest. Okay, so this is this is the Arabic. That's why there's an AL here. So this is from the Arabic for the original Greek title, which was the greatest. So the greatest, which was a book on celestial mechanics. It was a book on motion of the heavenly bodies. Okay, so this was the textbook on the heavenly bodies. Really, this was basically like the elements, except for astronomy as it was understood. Okay, so when this was written, this was the state of the art as far as astronomical consideration. So this was the elements, except for astronomy at the time. And so what's funny about this is Ptolemy also was into astrology. And so, he had no problem conflating astrology and astronomy, and this didn't prevent him from making all these computations and including all of this more objective stuff into both his astrological interests as well as this book. And so this was definitely like the textbook on astronomy prior to like the 15th, 16th centuries. This was the book. And so this book contains a lot of stuff. I'm not going to get into a ton of what this contains because mathematically I'm not interested in too much of it. What I'm most interested in is a couple of things. So one, Ptolemy also computed sine tables. Okay. We'll call them chord tables. That were basically trig tables. Okay. Ptolemy also used a number system based on Greek letters. It's pretty peculiar. Here's the list. So here's the table. This is Ptolemaic notation. And so to represent numbers, the way this was done is for numbers 1 through 9, we have alpha, beta, gamma, delta, epsilon, a letter F that Ptolemy used. This has actually been dropped from Greek previously, but it was reintroduced by Ptolemy, or at least he was a fan of it, I guess. Zeta, eta, and theta. Okay, that's 1 through 9. Okay, then 10 through 90 is iota, kappa, lambda, mu, nu, xi, omicron, pi, and q. Again, this is a thing that had been dropped from Greek earlier, but Ptolemy was a fan of this apparently. So then we got rho, sigma, tau. We have v or u, phi, chi, c, and omega. Okay, so this is 100 through 800, and so he could actually, using this, if he wanted, he could basically, for him, this allowed him to write any number that he wanted to. He could write the addition of numbers like this by juxtaposition, or he would just slam them next to each other. So for instance, if he wanted to write 11, this would be like alpha iota. Okay, it would be 11, right? It's 1 plus 10 or 10 plus 1. Okay, so if he wrote iota alpha, that's also 11. I believe he wrote smallest to largest though. So he wrote, he basically, it was like our place value. So it's like our decimal system, except the ones place would come first. Okay. So anyway, this was like Ptolemaic notation for keeping track of numbers. This leads to some pretty interesting things that we'll show here in a second. So that was how he wrote numbers. But when it came to this was how he wrote integers, I should say. But when he wanted to talk about lengths or angles, he used Babylonian notation. So, but he used Babylonian notation, which is what we use when we write angles and degrees. So he used Babylonian notation for angles and some lengths. So his Greek notation was really for positive integers. Okay. Right. So this is another thing that's interesting. So bringing back the table for a second. He uses omicron here for 70, but he used a little circle O that's very similar to this when he meant 0. Okay. So there's a little circle O here that denoted 0. Okay. And so if I were say expressing, so here's an example. of Ptolemaic notation. So let's say that I have like 120 degrees and 0 minutes and 0 seconds. Okay, how would he have expressed this? Okay, well, he would have expressed this as either kappa rho or rho kappa. So rho kappa, okay, and then this next length would be a 0, and then the next length would be a 0. Okay. Or if he was writing the chord of 1 degree, okay, this would be 1 degree 2 minutes and 50 seconds, or written as alpha, beta, nu. Okay, so let me bring back my table so that you can see what it is that I'm saying here. So 120 degrees here, this would be rho, which is 100, kappa, which is 20. Okay, and this centered circle would be the 0 placeholders for those slots, right? Computing the chord of 1 degree, writing this length as 1 degree, 2 minutes and 50 seconds. Okay, writing it like this would have been alpha for 1, the beta would be for 2 minutes, and the nu would be for 50 seconds here. Okay. So in doing this, he's taking the radius of the circle in question as 1. Okay. And so he basically had a decimal system, right? This was basically decimal notation where his symbols was that table, right, that I just showed, those Greek letters plus F and Q. Okay. And so this kind of shows like what has to be gone through in going through some of these ancient texts, where when you read a translation, sometimes you take for granted some of the things that have been moved over into more modern notation to make it easier. So I'm going to give an example later of like what an expression might look like. Okay, I'm not even going to write it out. I'm just going to show you what it might look like. So I'll do that here in a second. So next is Diophantus. So Diophantus, his name, if you are interested in number theory or if you are interested in cryptography, you've likely heard the phrase Diophantine Equations. So they are named for Diophantus. So he wrote a book titled Arithmetica, which was basically a book on number theory. So number theory, arithmetic, and really solutions to algebraic equations. So these algebraic equations, particular type that he was solving, would be called Diophantine equations. Now, Diophantus was interested in rational solutions to these, but typically when we say Diophantine equations, we're interested in positive integer solutions or just integer solutions to these equations. Diophantus was actually happy with rational solutions, period. So he didn't care, but typically when Diophantine equations are said, what we mean now is that we want integer solutions. So what's an example? So Arithmetica was in 13 books, so 13 chapters. Very similar to, identical to the elements, right? Same number. Actually, I think only 6 of these books had been recovered until the 70s, like the 1970s. So I think in like 1975 they found the rest of these, and so now Arithmetica is complete. But previously, up until like the 1970s, I think only the first 6 books were known. So what's some examples of some of the problems that he gives? So to divide a given number, which is the sum of two squares, into two other squares. So take a number, right, that is already the sum of two squares. That is, take two integers, square them, add them together. So that's a number that's the sum of two squares. Find another way of writing it as a sum of two squares. What is this? This is solving for x and y the equation x squared plus y squared is equal to a squared plus b squared, where a and b are given, right? And I'm trying to find x and y satisfying that. Okay. So in his special case, for this particular example, he uses a equals 2 and b equals 3. But the process he goes through here is actually generalized pretty easily. And so, in fact, he even gives an example that shows that you can pick the squares in question. If you start with 2 and 3 here, the other squares you can get are like 324 over 25 and 1 over 25. We'll get you there. So if a is 2 and b is 3, the other two squares you can get x squared is 324 over 25, and y squared is 1 over 25. Is an example of his method. Okay. All right. So to show you how he does this, here's the following. This is directly quoting Diophantus. Take x plus 2 squared as the first square and mx minus 3 squared as the second, where m is an integer. Say 2x minus 3 squared. Therefore, x squared plus 4x plus 4, that's expanding this, plus 4x squared plus 9 minus 12x, that's expanding this, okay, is equal to 13. Or that's summing the squares, right? Or 5x squared plus 13 minus 8x is equal to 13. Therefore, x is 8/5, and the required squares are 324 over 25 and 1 over 25. Okay. Okay. So that was his method for doing that. The question of how much algebra Diophantus actually understood is a big one, but there's reason to think that he understood a lot of implicit algebraic rules that he was using, that he didn't state them. He didn't state exactly all of the laws he was using, but it's clear that he understood many of them. So here is an interesting bit, and this is his notation. So here's an example of one of those laws that Diophantus probably understood when he remarked on 65 being a sum of two squares in two ways, since 65 is the product of 13 and 5, each of which is the sum of two squares. So he's claiming that I know that a number is a sum of two squares in two different ways, since it's a sum of two squares that are a sum of two squares. And that is saying that he understands this formula, basically. Okay, which is some algebraic rule, right? This is an algebraic rule. If you expand this, you get the same thing here, right? This is the idea. Okay, and so this is also a struggle of going through ancient mathematics and trying to understand what they understood, because they didn't always state all of their assumptions in a clear way like Euclid did. It wasn't totally clear exactly what list of common notions they were using, right? Okay, so Diophantus, he used this symbolic notation very similar to Ptolemy. He used the Ptolemy sort of notation here, where he did this to write out these algebraic expressions, and so we get kind of the first example of a really nicely standardized way of symbol pushing, right? This is a nice way of doing algebra with these symbols in a way that is very close to how we do them now. And so, plus was juxtaposition. Ptolemy did the same thing. Minus was this weird symbol. See if you can see that if I get it a little bit closer. It's like an logical and symbol with a straight line bar through it. And equals is this like vertical tilde. It's this vertical like squiggle. Okay. And so he wrote k to the v for x cubed, delta to the v for x squared. Zeta was for x to the first, or zeta zeta for the plural. Okay. M with a circle over it was for x to the 0th power. Okay. All right, so what is an example here? So look at this. Delta to the v, gamma, right? Gamma bar, if you like. M with a circle over it, iota beta bar. That expression is 3x squared plus 12. Okay, where's the 3 come from? That's the gamma, right? Let's flip back over. 3 is the gamma, okay? So 3x squared is this delta v, right? Delta v is x squared here. Okay, so 3x squared. M with a circle over it is this x to the 0. Okay. Iota beta is 12. It is, here's iota, right? 10. And beta is 2. So why do I have this m to the 0 here? This is my juxtaposition. I have to slam them next to each other with a placeholder here, right? And this is telling me that I'm adding these things. Okay, this is me adding these things. Okay. All right. Similarly, I have this crazy expression here, which if you trace through all these symbols that I went over, this is x cubed plus 8x minus 5x squared plus 1 is equal to x. Okay. Remember, there's my x, or there's my equal sign right here. Okay. All right. A funny thing that's recounted here, actually, that I'll just go through. So you might have heard the expression 1 iota of difference. It doesn't make a single iota of difference. And so there was a type of Christianity at the time that was pretty prevalent among a lot of the among a lot of Europe. It's called Arianism. Okay, and so when Athanasius was defending the divinity of Jesus against Arius, one of the central tenets of Arianism was this kind of duality thing where Jesus was like God but not equal to him. The difference between the like and equal was the difference of a single letter, which was the letter iota, and today we distinguish this difference by the linguistic difference between homeomorphism and homomorphism that I'll talk about a little bit later in the course. But this is also the origin of the phrase not a single iota of difference. If you hear something saying it doesn't make a single iota of difference, it's because the letter, the difference between equal and like was a single Greek letter. Okay. One more thing, and then I'll be done. So, by the time of Pappus, it was a sad time for math in Alexandria because the famed school of math in Alexandria, the thing that Archimedes had been associated with, the thing that even before Archimedes, right, had been established all those years ago. I mean, Euclid, right? Euclid of Alexandria was one of the first one of the first great directors of the Alexandrian school of mathematics. This Pappus was literally like the last and only member at the time. And so Pappus was writing his major work, which was titled the Collections, which was mostly a collection of previous results. But it included, in Book 7 of the Collections, a theorem known as Pappas's Theorem. The Theorem of Pappus, or Pappas's hexagon theorem. So when Pappus's name is brought up, this is typically the context in which it's brought up. He states a theorem that he uses the theorem of Menelaus to prove. Okay, so uses theorem of Menelaus to prove. He didn't realize it at the time. That is, Pappus didn't realize it at the time. But this theorem was actually really, really important for a number of things. It is geometrically extremely important in what's called projective geometry, which I may mention a little bit later in the course. It is also equivalent in a way to commutativity for multiplication. This theorem was used by David Hilbert in his axiomatization of geometry. So remember we mentioned Hilbert in the context of his finishing Euclid's attempt to make the Euclidean style geometry completely rigorous. So Hilbert actually used this to show that you can bring in commutativity of multiplication from the geometry. Okay, so you can actually construct commutativity as a result of the geometry rather than the other way around. So I'll try to talk a little bit about that, but I think I've run out of time here, so I'm not going to state Pappus' theorem until next time. So I believe I'll stop and I will finish this up during lecture next time. So anyway, have a great break. I'll be posting some stuff soon. Your first exam won't be till after break, so you'll have plenty of breathing room. When you get back, we'll talk more. We'll talk more about it then. Okay, so just relax and have a good break, and I will see you all. I guess not next week, but the week after.